Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome in to our viewers from around the world. Thank you for joining us. Please let us know where you're watching from. And also welcome into listeners on the podcast version of SETI Live, available on most podcast platforms. Today, I am here with Dr. Amanda Steckel, who during her doctoral work at the University of Colorado Boulder, figured out that Mars had rain or snow or some kind of precipitation, which is really amazing. We know Mars had water, but this is actual evidence of that climate and the climate changes that have happened since then. So today I am happy to have Dr. Steckel with us to talk about her research. Welcome in. Thank you for joining us, Amanda.
Thank you. I'm happy to be here.
So I just have to fix one thing on my computer screen that went really wild while I was getting set up here. And so you did this as doctoral work. You are now a postdoc at Caltech, correct?
Yes.
Okay. All right. So let's talk about this. Are we talking like blue skies over Mars? For those of you who know Total Recall, you'll get my reference. Are we talking serious rainstorms, serious snow? What kind of weather are we talking about when it comes to what you figured out about Mars?
Probably not big thunderstorms, probably not beautiful blue skies. But basically, we have evidence that there's an even distribution of the elevation where valley heads originated from. And I think it's hard to explain that without some form of precipitation going on for some amount of time. In this paper, we postulate around on the order of 1 million years. I modeled 600,000, so something on that order.
Okay. So let's take it back to the beginning a little bit. Let's lay the foundation here. So why Mars? What is it about Mars? Why are we studying its past climate? What is this research? What's the focus here? What led into it?
Yeah, so Mars is really old. And what's great about Mars is we don't have the tectonic recycling program that we have on Earth. So we can actually see those rocks that are 4 billion years old, which we don't have access to on Earth anymore. And there's also this evidence on Mars, as you mentioned in the beginning, of a global climate change, which is unique, pretty unique. We don't often see that in planetary systems. So that's a really compelling area to study. And then, of course, there's the third piece, which is everyone's always been interested on if there could be life on Mars, and water is a critical component of that. So those three things combined is sort of why we're studying this 4 billion year old time period on Mars.
Okay, so we're looking at Mars, we're looking at the past. So what is your study? What did it look at? I understand this is computer simulations, and so let's kind of, for everybody, talk about what the study was, what it looked at, and how your computer simulations worked.
Sure. So we see evidence of water on Mars in the form of valley networks, which look like, think of the Grand Canyon, something like that. Basically erosion from water into rock, forming these long valley networks. And there needed to be some amount of liquid water to do that, but we don't know what the origin of that liquid water is. And so that's what the study was focusing on. And what we wanted to figure out was, could that water have come from ice caps, from like a very frozen, barren climate that occasionally had something melt and provide water? Or did that water require some amount of precipitation? And to do that, the landscape evolution model that we developed is using a software called LandLab, which was developed at the University of Colorado Boulder by Greg Tucker. And basically, we are taking a simulation of the landscape representing somewhere on Mars, and we are applying a grid. And then we are applying physics to each node of the grid and saying, basically, based on where I put the water, now you go ahead and you erode for 600,000 years, and then what the surface looks like afterwards. And what we found is the case where we have ice caps with water being supplied at a certain altitude, that all of the heads of the valley network start there. So the water doesn't flow downstream and then start eroding a valley later on. It really seemed to start around that elevation, and then versus the condition where we have water all over the surface representing some kind of precipitation. And as you said, that might involve rain, snow, ice, some combination of the three, winter mix, not sure which. So the other thing we did is we compared those two models to what we actually see on Mars, to the data from the surface. And I did a study basically of the equatorial band on Mars, and a big region, positive 20 degrees latitude to minus 20 degrees latitude from the equator, and mapped out the elevation that the different valley heads originated from. And what I found is that from around minus 1,800 meters to positive 3,500 meters, there's a pretty even distribution. And I think that that's hard to explain without using some kind of precipitation to move the water around. But that's really where the extent of the study was. What we would invite next is for people to model the climate and see if they can reproduce these results.
Okay, well, that's kind of interesting to me because one of the things I've sort of heard like as a theory about Mars sometimes is that like it was covered in water. It might have been covered in water. So you're saying that it could have been, but not because of say like some global ocean, but more just the general water precipitation effect rather than just, oh, it's a water world and all the water went away.
Yeah, we're looking at the distribution of where the water was relating to elevation. So when you model glaciers and where they're located, we come up with what's sometimes called an ice stability line. It's a certain altitude above which ice can then start forming. And a lot of people have done that on Mars, and Mars is a bit complicated because we also have the spin axis of Mars tilts with respect to the sun over time. So the obliquity is what we call that, changes. So we do have some movement of where the ice is being put if you assume some ice stability line. But even with that taken into account, I think these modeling results show that you wouldn't expect an even distribution across all of the altitudes. You would expect there to be some kind of peak around an altitude where you have ice melting from an ice cap. That doesn't mean that there were no ice caps ever. I actually think we might see some in the really extreme high altitudes along the rims of some craters. But there's probably a combination of a more complicated climate history going on. And this study is basically saying that some period of time, some periods of hundreds of thousands of years, I think we had to have precipitation just to cause this spatial pattern that we're seeing.
Okay, well, I want to talk to you more about this. Obviously, I'm going to welcome in people that are watching. Let's see. We have a fairly global audience today. We have some people from India, here in California, not very far from here, and also a little bit further away from here, New Hampshire, Colorado, Florida, Berlin, Boston, Wisconsin, Turkey, and France. So yes, getting quite the global audience. Thank you everybody for joining us. We are talking about Dr. Steckel's study that looked at precipitation on Mars using computer simulation studies and models, and figured out that yes, it was probably rain or snow or ice or some combination thereof that carved some of these features that we are now studying more close up, some of it. So let's kind of go into that evidence of ancient precipitation. What you're kind of related this to the Grand Canyon, but the Grand Canyon is sort of that river flow eroding carving. So what is more of an analog here on Earth, you think, to what happened on Mars?
I think there's a lot of river networks on Earth that could look similar. We didn't actually focus on Earth analogs in this study, but you can think of what we call it is a dendritic finger-like pattern is what we see on Mars. And that's a big part of the evidence of why you need flowing water to carve this as opposed to like something like a glacier. You can count what we call branching ratio, which is how many pieces of the network split off, and look at the sinuosity, how curvy it looks. And taking all those things into consideration, there's a lot of similarities between the global network of valley networks on Mars and what we see here on Earth. And in the study, I also looked at 7 in particular, and we really focused in on the area that has the most likelihood to have been warm and wet, because we're trying to look at sort of the extreme case. So we looked at some of the longest and most branchy and sinuous networks in our study.
You're really kind of pulling some of my basic geology knowledge out here when you said that. I was like, oh yeah, no, branching ratios. I remember calculating some of these. Okay, so when you say dendritic, just for clarification for the audience, think of like the dendritic is basically referring to the veins in a leaf, right? So if you hold a leaf up to the light and you can see all the veins coming kind of out of like the main part of the leaf itself, that's what we talk about when we say it has a dendritic shape. It's there's a main piece to it, but there's also all of these branches. So when it comes to rivers, I would say, would you say something like, you know, the Mississippi, the Missouri, these are definitely like these large rivers with lots of branches out from them?
Yes, something like that. But we didn't look specifically at aligning them with one of those.
Right. Okay. I just want the audience to be able to sort of like visualize what we have going. So how would rain or snow affect these features? I know how they would here. Is there a difference between what happens on Earth and what might have happened on Mars?
Actually, what I found was less than you think, although on Mars we have a lot more uncertainty, of course. So there's a stream power incision model is what it's called, a basic physics model of how you erode, how water erodes rock to form those types of shapes. And what we did in this study is really focus on the very simplest case, because there are so many unknown variables. The exact erodibility of the rock we're targeting, the exact precipitation rate 4 billion years ago, for instance, and then the time that this formed over. So we sort of had to group those together. And the approach I took was to try to model what we actually see. So I took reasonable numbers that were sort of in the middle of what we see, and then just got an incision depth matching the actual data we have on Mars, and then went from there with the modeling. And that's also why we took 2 different sort of extreme climate scenarios. Neither one of these extremes, like warm and wet versus icy cold, are the probable answer. There's probably a more complex picture with multiple periods of maybe being drier and wetter. But by using a computer simulation, it's much easier to get actual results out when you have 2 sort of extreme end members, is what we call them, to compare with, because we just don't have all of the details.
That makes sense. You're basically taking it down to first principles, essentially, is what you're doing. So this is a very complicated physics, geology, chemistry problem, and you're trying to say, okay, on one end we have this, on the other hand we have this, and neither one is probably right. Somewhere in the middle. So much of science is reconciling your endpoints. So I totally understand. How is this? What data? I'm going to back up a little. What data did you use for this? So I know you're using a computer simulation and you're doing modeling. Where's the data coming from for Mars?
We mostly used laser altimetry data that made a digital elevation model. So it's sort of the topography, the relief, and that's measured from, you know, a satellite in orbit firing a laser, and you measure the time of flight, and from that you can get really good resolution on what exactly the elevation is on the surface. And that's most of actually what this study used. The interpretation of the study, though, I should emphasize, relies on lots of other work that's been done before, looking at things like the chemistry, like you mentioned, like fine scale images from rovers, looking at little laminations and pebbles that you can see from that look like they were eroded in a stream bed, and other things you can see from satellites like fans and deltas. So you can't, this is, by itself doesn't stand alone as like the evidence of precipitation, but if you take this alongside all those other pieces of evidence, that's where you start to build up a clearer picture.
I do think that seems to be like the picture that we are building. I've noticed, especially recently, a lot of the research kind of coming across my desk is all sort of coming together. You know,
yes,
water on Mars was kind of an amazing concept 20 years ago. Now it's like Mars had water. We're just trying to understand how it had water at this point and what that water actually did on Mars, and also like how it went, where it went, because that's also another part of the puzzle that we're asking. So, you're what?
Yeah, and that's the part of this that I'm excited for is I'm hoping that this data set becomes a nice tool that people can use in climate models to reproduce.
Right.
And I think that that's like the real value of this project is not just the idea, but also like having quantifiable data so that we can get numbers and try to put some of this stuff down. I agree with you that we're sort of coming to a consensus in the community over time, and we just need a few more pieces to get there, I think.
So, what's the implications from a SETI standpoint? What's the implications for windows of habitability on Mars? This is something that I talked about earlier,
Yeah.
that we've talked about earlier in other shows. But these windows of habitability, that for warmer, wetter. These are things we say we need when it comes to life, right? We need warm, we need wet, we need some sort of like chemical soup that we can kind of work with here. What's the implication of what you've sort of modeled for habitability on Mars?
Right. Yeah. So I think that you've already addressed this in some of the other shows you've done, but we have all the other components, the other elements, like you said, and the energy, we think, the chemistry, the pieces that we need for life. I would say that there's we need the water on Mars, and that's sort of what this is trying to address. But the other question is, how long does life take to form? And on Earth, I've seen some people postulate that maybe it's 1 billion years or 1.5 billion years, something like that, based on the data points we have from one planet, which is Earth.
Right.
And if we could find information about this on Mars, so for instance, as an example, this study is saying maybe it required 100,000 or 1 million years to be wet on Mars. And then if we found life, that might give us another data point and say, well, maybe life doesn't take quite as long. That's a big if, and I should stress that this study is not really getting at the evidence for life. That's really what the rovers are working on now, and that's really Perseverance and Mars Sample Return would maybe supply that evidence. But what's exciting about Perseverance, and I'm sorry, I might be jumping ahead a little bit because I got a little excited, but Perseverance is up on a crater rim now, and we're looking out at this terrain. And some of it is Noachian terrain from this time period. So I do think that's a really exciting opportunity to try to get ground truth of what the climate was like. And if there are biosignatures there, that would be really exciting.
So
and understanding how much water is a critical piece of that. Sorry.
Right. So let's talk a little bit. I think I just want to kind of clarify the timeline we're talking about. So our solar system's about 4.5 billion years old. As you said, we can't see the rocks from that as far back as that 4.5 billion years because of our plate tectonics, because of the rock cycle. Going back to some of those first principles in geology, rock is made, rock is changed, rock is kind of changed further and destroyed. Okay, cool. And then we have more rock. So, but on the front of like how long it took, you talk about the Noachian period for Mars. What does that translate to time wise? Time ago, that kind of thing. What are we talking about?
Yeah, so this time period was around 4.1 billion years to 3.7. And we got that from a technique called crater counting. And it's comparison to the number of craters that hit the moon. Maybe your listeners already know all of this. But it's not an exact time frame. That's sort of our best estimate right now. And we also do have a few meteorites from Mars, but we don't know exactly the spot they came from. So if we could get samples back, actually, we may even be able to constrain exactly the time further through different radioisotope dating techniques. Sorry, I got a little bit excited. I work on the Mastcam Z instrument now for the Mars 2020 mission. So I guess I'm a little bit excited about it. I keep bringing it up.
No worries. The excitement is why you are here. The
Yes.
Excitement translates. So anybody who is excited about science, I am all for. So okay. So how is this shaping the work that you're doing with Perseverance? I know we now have two rovers kind of at the top of their craters. So this is kind of amazing. Curiosity got out of Gale crater, and Percy has made it out of Jezero crater. So how is what you worked on as a doctoral student influencing the work that you're doing now at Caltech and JPL?
Oh, it's super helpful because I'm basically studying the same period of Mars time now, except I'm using it through different new techniques, additional techniques, which is really exciting. So I'm looking more at the composition with multispectral data from the Mastcam-Z instrument, and I'm also looking at some satellite data and correlating between the two. HiRISE, which I think is an instrument you're very familiar with, is one of the ones I'm looking at. So that's what I'm working on right now, and I'm trying to understand different units that are in this Noachian time period, and trying to support the Mars 2020 team and give them information of exactly what are we looking at, so that they can decide, well, what do we want to sample? What is our priority? And understanding what the history of precipitation might have been on this period of time is also a really important part of that judgment call of understanding, well, what is our priority? Where do we think we're going to have biosignatures? Because that's really the goal of the Perseverance mission, is to get samples from their most likely spots to have biosignatures.
So basically what you're saying is this would benefit from the Mars sample return.
Yes. Yeah.
So Perseverance can do only so much in situ, and are you part of the selection for what targets are, like, oh, that would be a great rock to like drill into and kind of get a sample from, or what are you specifically kind of like dealing with here?
I'm specifically on the Mastcam-Z instrument team, and I'm like I get to go to those meetings, but I'm not the decider of anything important. But what is fun is, yes, you mentioned Mars sample return. We've been caching these samples, and they're really exciting. And it is fun to sort of see that process happen. I'm really having a blast getting to listen in on the team and help where I can. I do think this cache that we're coming up with, especially the one that's in the body of the rover, because we have a couple different ones. We have some that we left sort of on the surface, and then we have some that are cached inside the rover. And I think that that's a really exciting kit to try to get home. And yeah, if there's anything I can do tactically to support a decision of where in the Noachian we can go, that is something I'm trying to work on. I'm not sure I'll get the answers there fast enough, but we'll see. So, and I also help with the uplink and downlink of the instrument, that type of stuff.
Fantastic! It sounds amazing. You are to use a phrase, you are in the room where it happens, and that's pretty exciting right there. We have a couple audience questions. One slightly more. Okay, we were kind of talking about this, of where your data came from. Did you get any real-time data from the Mars rovers for the study at all? Or what kind of data would you like to get in the future to study this? So how did the Mars rovers work with what you've done and what you want to do?
So for this study, we didn't use any data from the rovers. We used satellite data from a laser altimeter that measured like really precise elevations. But we do compare our data with other rover information in order to get the context to make the interpretations we're making. And so we compared our data to data from all the way back to the Spirit and Opportunity rovers at home base that looked at these fine scale laminations that we saw. And the Curiosity rover, and as well, has taken some pebbly conglomerate images that we've looked at. Those pieces of data provide really important context in order for us to interpret what we're looking at. But for this study, we really focused just on the laser altimetry data set.
Okay, that absolutely makes sense, and I like that it's very specific. So what is kind of like next for you? You're in your first postdoc. What's the plan for Dr. Steckel going forward?
I'd love to know. No, I'm kidding. I
Fair,
am
fair.
spending half my time right now working, as I said, on the Mars Mastcom-Z instrument and working on a science project related to that, and also helping out with a little bit of the operations. And then the other half of my time, I'm working on studying the moon, actually. And I'm working on a mission called Lunar Trailblazer. And I'm also working on just a data analysis project with respect to water ice on the surface of the moon. So I really enjoy studying planetary surfaces, and I want to continue to do that. So my background, though, what got me into planetary science is I actually came at it from the engineering side, and I actually used to design instruments and design satellites. And so I actually want to find a way to sort of wrap back around and work with some of the mission formulation or instrument teams on new concepts, because that's where I think the magic will happen. I think that's the really exciting frontier to start working on. So that's my long-term goal.
I like it. I like it. I like tying everything together in your own career is always kind of an amazing feeling. I definitely feel that for myself with some of, like, I've done PR and now I'm doing communications and I've done science, and putting it all sort of together. It makes you feel like maybe I didn't waste my time on things. Okay. So, oh, someone's watching this from Australia now. That's really neat. Thank you. Rob Harrison asks, and I guess we need to kind of clarify this. A satellite orbiting Earth, but no, you're talking about the ones orbiting Mars. So Mars
Yes.
has a whole host of satellites going. HiRISE, the camera that you mentioned, that's on board the Mars Reconnaissance Orbiter.
Yeah, and also used, sorry.
Yeah, no, go ahead.
Oh, and we also use data from MOLA, which is the Mars orbit. It's also on the MRO, the Mars Reconnaissance Orbiter. Exactly. Sorry, you had it right.
I'm not familiar with all of the instruments. HiRISE, obviously, because I've seen my colleagues working on it, but also we share a lot of images from the HiRISE mission, obviously. So okay. So we're talking, when we talk about she's using satellite data, you're using satellites that are in orbit around Mars, of which there are kind of a host at this point. So it's pretty neat between all of the rovers and the orbiting satellites. The amount of data we get from Mars is astounding, and yet please send a sample return mission. Okay.
Yes. Yeah, and one more little piece in defense of a sample return mission, if I may. When we're looking at Mars from orbit, although we do have several satellites that have done this, and it's really exciting, we have dust in the way of when we try to measure the surface. And there's times where we can pierce through it, or it's moved away because of weather patterns. But there's also times where we might be missing a lot of context and information. And that's part of the importance of the rovers, is really being able to use a brush to scrape that dust off and actually see what's underneath. So that's part of why we have to sort of take multiple approaches when we do exploration. There's not really one technique or one instrument that'll get you the right answer.
I think that's definitely very true. There's a lot of angles that need to be put together. And as a reminder to our audience, Mars has some weather. It's not a lot. It's 1/3 the gravity. It's a much thinner atmosphere. But there is weather. So there are dust storms. There are dust devils. There's there are things happening. It's not quite the dead planet that we thought it was. It's not full of Martian canals, like that, not designed by Martians, but yes, there is a lot of stuff going on there. Rob is asking how many satellites are orbiting Mars and are there live cameras? There are no live cameras. That is really hard to do. It is a long transmission time and a lot of data that has to go down the pipeline there. As far as how many satellites, I'm actually not sure. I can think of at least 3 off the top of my head, but it's probably closer to 4 or 5.
And other countries have been contributing more too recently. Yeah, so I'm not quite sure.
I'm thinking of, like, there's MRO. There's I'm pretty sure China has one. I know the UAE has one. So there's been a lot, and a lot of countries participating and doing their own science, which is great. So yeah. It's quite a few, but no live cameras, unfortunately. Live cameras are very difficult from other planets. Maybe someday we'll figure that out, but right now, not so much. So Amanda, is there anything I missed that you wish I had asked you about? Is there anything you want to
I don't
mention?
think so. I just want to, I mean, I hope I got this across, but planetary exploration is such a cool, dynamic field. And I sometimes people I think we've already figured everything out that there is to know, and that's just not true. It's like we're explorers being put in the middle of nowhere on Earth with very little contextual information. That's really what we're like on these other planets, where we just have very limited data and we're trying to piece things together. So it's a really fun, challenging field to work in, and there's so much more to study.
All right. Well, fantastic. I do see there's a question coming in about elemental sulfur. Stay tuned. We will be talking about some more rocks on Mars and things that we found in the coming weeks. So yeah, thank you, Amanda, for being here. Congratulations on your first authorship and your paper and finishing your doctorate and getting that first postdoc. That is a lot, and it's amazing. And in the middle of all that, you moved too. So
Thank
the
you.
life of grad students and postdocs, everybody, I think, is underappreciated in its stress levels and accomplishments. So
Thank you.
congratulations, and thank you for taking time to come and talk to me. Your enthusiasm is infectious, and let me know when you have new things to talk about, and I would love to have you back on the show.
Thanks. Thanks so much.
All right, everybody, thank you for watching. As a reminder, the SETI Institute is a 501c3 nonprofit organization. We exist and we can do this because of donations from people like you who are watching and listening. So if you have a moment, please check out our website, SETI.org, and click on that bright red Give Now or Donate button, whatever it is labeled this week, and drop a few dollars in so that we can keep doing these shows and bring in such enthusiastic people like Amanda. I mean, it's so wonderful. And thank you for your questions. Thank you for being here. Thank you for watching from around the world. And we will be back next week. I'm going to be talking about a cookbook for life. So we're going to focus a little bit on chemistry and evolutionary biology. So I have some reading to do. And then it's going to be talking about an update on the Laser SETI program. And then starting into June, we have more stuff on Mars and Titan. So stay tuned, everybody. Great shows coming up. And we will see you all back here. And thank you. Oh my gosh. Thank you so much for the super sticker. Much appreciated. And we will be chatting with you all next week. Thank you again, Amanda. And thank you, everybody, for watching. Bye now.